Okay, we are going to have the last section here of chapter 1 on inverse functions. We need to know by the end of this section how to find inverse functions, what their relationships are to each other, how to verify two functions are inverses, and things like that. So first we have function f of x is equal to 4x. We need to find the inverse of that and then verify that f of f inverse, so that's that composition that we did in section 5, and f inverse of f equal the identity function. So that notation, that f to the negative 1, that means f inverse. So our steps here to finding an inverse, the first thing we're going to do is instead of using f of x as the notation, we're going to use y back in the original. And then the first step to finding the inverse is to switch variables. So we are going to switch it to x equals 4y and then solve for y. Once you solve for y, you're going to have the inverse. So all we need to do on this section, or on this question, is divide by 4. Once you get y by itself, we're going to use the correct notation. And that is the inverse. Now, there is a way to verify that we did this correctly, and that is with those compositions. So we need to do the composition f of f inverse, that is taking our function that we just found and plugging it back into the original, and taking the original and plugging it into this function. And if we get the identity function, which is just x, if we get x when everything is simplified, then we did everything correctly. So starting with f of f inverse, that means I'm taking the function I just got, x over 4, and plugging it into 4x. So here the 4's would cancel, and I'm just left with x. And then I do the composition the other direction, which is f inverse of f, meaning I'm going to take the original 4x and plug it into x over 4. Again, the 4's cancel, and we get to x. So they are, in fact, inverses of each other, and that's how we verify that. Well, let's do it again. Find the inverse of x minus 6 and then verify that you have the identity function when you do the composition both ways. First step is to put y in instead of f of x and switch the variables. Get y by itself and change it to inverse notation. Then we do the composition to verify that we did it correctly, starting with f of f inverse. So we have the x plus 6, or plugging in the x spot in the original. I put that in parentheses so you could see what I was doing. These 6's cancel and we get down to x, and then the other direction, oops, f inverse of f. So I'm taking the original, x minus 6, and plugging it in for the x in the inverse. And again, the 6's cancel down to x. So those are pretty simplistic examples. The simplifying steps are going to be a bit more complicated as we get a little bit more complex equations, but that's just to show you how that works. Speaking of more complex, here we go. We have a cubic function and we have a cubed root function. Show that the functions are inverses of each other. So if they're claiming that f and g are inverses, then we would need to do f of g of x and g of f of x. And if we get x both times, if it simplifies down, then we did it correctly. They are inverses of each other. So let's start with f of g of x. That means I'm going to take the entire function g and plug it into function f, where the x is. Cubed root of x plus 1 over 2. That whole thing is going to be cubed. minus 1. So we kind of have to work our way inside out here for simplifying. We need to cancel the cubes. So everything is still there except for the cubes. And then we need to cancel the 2's. And it, of course, gets down to just x. Now when I go the other direction, where I take function f and plug it into function g, where the x is, the simplifying steps are kind of going to be the opposite of the steps we just did. So the last thing we did in those black steps was we got rid of the 1's, but that's going to be the first thing we do here because that's the first thing that simplifies. When I got rid of the 1's, now we need to divide the 2's. And then all I have left is to simplify the cubes. So kind of interesting how when you do the composition the opposite direction, your steps are opposite. So instead of doing cubes, then 2's, then 1's, we did 1's, then 2's, then cubes. Cool. So does every function have an inverse? No. So we need to know first how to figure out whether it has an inverse or not. And this is the fancy math definition that a function has to be one-to-one, in which no two elements in the domain of f correspond to the same element in the range of f. That is confusing. Even the definition of one-to-one, a function f is one-to-one if for a and b in its domain, f of a equals f of b implies that a equals b. That's also confusing. The method that we're going to use is the horizontal line test because we have a graphing calculators at our disposal, and this is going to be the easiest way, even visually, we'll be able to tell whether a function has an inverse using this. So on a graph, it's easy to tell if a function is one-to-one, simply seeing that every horizontal line only intersects the graph once. So we'll just draw a line through our function and say, okay, does this hit more than 1 point? If I was to draw a horizontal line anywhere on this graph, would it only hit 1 point? If the answer to that's yes, then it is one-to-one and it has an inverse. So when it's asking, is a function one-to-one, really it's just asking, does it have an inverse or does it pass the horizontal line test? I'll just do HLT. So what we're going to do is graph it so we can tell whether or not it passes. Let's get our calculators out. Square root of x plus 1. That plus 1, and make sure it's on the outside if you have the older style calculator where you need the parentheses. Zoom 6 to make sure we're in a standard viewing window. And it looks like this. So it is always increasing. It hits at 0, 1 because there is that vertical shift up 1 of the basic square root graph. So the question is, does this pass the horizontal line test? If I was to draw a horizontal line through anywhere, would it ever hit more than 1 point? Since it only hits 1 point at any time, then yes, it passes. So it is one-to-one. So this is what we did algebraically. First, we need to decide if it has an inverse. We're going to use the horizontal line test first. And then these are the steps that I showed you on the first couple examples, where we put y in for f of x, switch x and y, solve it for y, and we can, this number 5 step is kind of optional. It's if you're not sure you did it right and you're, somebody who likes to check their work if you can. Number 5 is a check your work kind of situation. If you want to know for sure that your answers are right, you can do the compositions and see if you get the identity function of x when you simplify them. Okay, so let's find the inverse of 5 minus 3x over 2. The first thing we're going to check is if it passes a horizontal line test. If it doesn't, you're done. You don't have to do anything from there. Okay, so we have 5 minus 3x in parentheses, all divided by 2. Now this is just a line, so it definitely passes the horizontal line test. So we know that it has an inverse. So our first steps then are going to be to substitute y in for f of x and switch the variables and solve it for y. So the first thing I'm going to do is get that 2 off the bottom by multiplying both sides by 2. Subtract the 5 and divide by negative 3. So make sure that you do not leave your answer in terms of y, because it's technically not y. We just use that to help us out. This y is representing the inverse. So make sure that you do that or you can lose some points, kind of like an incorrect label. All right, next one. Find the inverse of x cubed minus 4. Let's see if it passes the horizontal line test before we even bother doing any algebra. X cubed minus 4. So this is one of those cubic functions where it looks like it might be constant, it might go back down, but it doesn't. That's still always increasing, just very, very slowly there in the middle. So this does pass the horizontal line test, which means we can proceed with our algebra steps. Put the y in, flip them, and solve it for y. And then, of course, make sure you put f inverse in instead of y. There is something of note that we can talk about. Let's talk about it on this next example here. There is a special graphic relationship between f of x and f inverse of x, and that is that the function and its inverse are going to be perfect reflections over the line y equals x, which makes sense because we switched the y and the x and then solved it. So to have that reflection makes sense, but that's a good way for us to check our work as well, to make sure that when we're done, we can graph both, and if you see that reflection over the line y equals x, then you know you did it correctly. There are times that our answer is not going to perfectly reflect that, so we need to maybe restrict the domain. In this example, we do need to restrict the domain, so that is something to check at the end. First, we're going to verify that this passes the horizontal line test to make sure we can even do it. 2x minus 3, parentheses over the whole thing. Okay, so I am going to graph this time, since we're talking about the graphing relationship. Looks like that. Okay, remember I mentioned that the function and its inverse should be reflected over this line, y equals x. I'm going to put in here as a dashed line. So we know this passes HLT, so we can continue on finding the inverse. Substitute the y in. Switch the variables, which is why they have that graphical relationship of the reflection over the line y equals x, and solve it for y. So we're going to need to square first to get rid of that square root, and divide by 2. So the f inverse is x squared plus 3 over 2. Now let's graph that, since their relationship is that they should be reflected over the line y equals x. Here's that line. I drew that in on our page as well. And make sure that these are in fact reflections. So notice that our green function over here it's like a half a parabola, but when we found the inverse, it was a full parabola, right? It's up here. Let's see if I can do a good job. It's pretty close. So if I cover up the left half of that parabola, I can see pretty well that the green is a reflection of the red and vice versa, but I don't want that left half of the red parabola. So what I need to do then is restrict the domain of my answer and say that x has to be at least 0. And when I do that, this piece kind of just goes away when I restrict the domain, so that it's only the red half that we want to match that green half. Okay, so that was finding inverse functions. Here is our homework, and we are done with chapter 1 for pre-calculus.